All right, let's get started. The topic of this video is going to be something called confidence intervals. Confidence intervals, it's a relatively important concept for your analytical chemistry class. I would rate it at least an importance of 3.5 out of 4 stars. It's pretty likely you're going to encounter a problem based on this during your semester exams and also during your standardized final exam. I mean, it really approaches a 4 out of 4 star type importance. It's pretty common to see this type of problem. So we're going to talk about what a confidence interval is and then what you need to know about it. Okay, it's actually real important that you understand the really the definition of what a confidence interval is, what its meaning is, and then also how to find it mathematically. There's really a two-part problem here. Okay, so let's start with the definition. A confidence interval is a range about a mean within which there is a specified probability of finding the true population mean. That definition may not mean a whole lot to you right now. It's a little bit confusing, okay? But we're going to break it down a little bit and explain it in a little bit more practical terms. Let's just hypothetically say that you're measuring a solution and you know the concentration of the analyte in the solution is exactly 50 millimolar or 50 millimoles per liter. That's the true concentration. That's what it is. But when you go into the lab and you do your replicate analysis, maybe you do n equals 5 replicate analysis, you don't get the exact same result each time. And on none of these cases do you get the actual true result, 50. Sometimes you're a little high, sometimes you're a little bit low. And this is, of course, very common. It's very common that you're not going to get the exact right answer whenever you do the analysis because of random error. Sometimes you're high, sometimes you're low. Now, if we average all these together, we hope that our mean is pretty darn close to the true concentration. And in the absence of systematic error, that should be the case. Okay? Here, if we average these 5 together, we get 52.1 millimolar, a little over 52. So we're reasonably close to 50, but even our mean is not exactly 50. Well, why is that? Well, because each one of these data points has random error reflected within it. Sometimes a little high, sometimes a little bit low. So it makes sense if you average 4 or 5 imperfect numbers, that the average you get might also be imperfect. There's no guarantee this average is exactly what it should be, and in this particular example we see that it's not. So how are we going to deal with this? This is a bit of a problem. Well, we can define a confidence interval about this mean, which is going to be a range of numbers. Maybe 52 plus or minus 7, say for instance, hypothetically. And if that is a plus or minus 7 confidence interval, our true mean would lie between it. So if we define a range of values instead of just one mean, we can start to say with a given probability that the true mean lies within that range. And that's what a confidence interval is all about. It basically creates a range of values about our experimentally determined mean that we can have some confidence in finding the true concentration. Okay. Now what we're going to talk about is rooted in random error. That is that randomness of data up and down about the mean. If systematic error is present in your analysis will always be incorrect. It will always be wrong. What we're going to talk about with respect to confidence intervals and having some specified probability of having the true mean within the range, that only treats random error. So if your analysis has systematic error, your answer will always be incorrect, always be wrong. That's an important limitation of what we're going to talk about, all right? Another thing that I want you to concentrate on is really understanding this definition of what a confidence interval is. It's this range around the mean, which there is a specified probability of finding the true population mean. The true result is the true population mean. The measurements is just 3, 5, however many replicate analysis, and we're going to get an average from that, but that's not the true accurate value. This is the true accurate value. This is just our experimentally sampled measurement. Okay, so it's important to understand what these terms mean and what this definition is. Okay, it's actually really important because you might think that you're only going to see a quantitative problem on this, but oftentimes you don't. You see conceptual problems, and you need to know the definition. You need to know the limitations of this. To answer the question correctly. So you have to think about things at a little bit deeper level than just plug and chug computational stuff, all right? So none of the measurements are exactly 50, sometimes high, sometimes a little bit low. Because we take a limited number of data points, it's unlikely the data set mean will be exactly equal to the truth because of our sampling error, as I like to call it, okay? So how are we going to fix this? Well, we can fix this problem by defining our range, that is our confidence interval of values the true mean should lie within. So we're going to make a range around the mean. Mathematically, how do we achieve this? We do so through using this equation shown in the center of our slide. You will need to commit this equation to memory because, again, very likely it's not common that equations are given on your standardized exams. So consequently, you're going to need to know this if you have to work a quantitative problem. It's not too difficult because the confidence interval is equal to the mean of the data set, this is the average of the data set, plus or minus t times s divided by the square root of n. The square root of n is the number of measurements in our data pool. S is the standard deviation of the data pool. The x top hat is the mean, and t is our t-statistic. We're going to get that number from a table. I'll show you such a table in a few minutes. The table would be given to you on an exam. You do not need to memorize it. So armed with this equation, we can actually work a sample problem to compute or calculate our confidence interval. So let's do that based on the data in that previous example. Just to remind you, the true concentration was 50, and these were our 5 replicate measurements. We take the average of that data pool, we get 52.1, and the standard deviation is 2.2. So I'm just going to copy that information right here for the purposes of our computation, okay? In this particular example, I would like to compute the 95% confidence interval. 95% confidence interval. Remember on the previous slide I talked about the confidence interval being a range of values within which we have a specified probability of finding the true population mean? Well, this is going to be our specified probability here. It's 95%. I could make that 90%, I could make it 99%, 99.5%. And the only thing that would change about the calculation is the number that we use for our t-statistic, which is right here. So we'll see that here in a second. Okay, but for this sample problem, let's just choose 95% confidence interval. That's a pretty common example. Okay. So to finish this off, I need to write my experimental mean, and I need to define my range. So I do my plus and minus bit, and I do my fraction. Now since we had 5 replicate analysis, the square root of 5 goes in the denominator. We know our standard deviation was 2.2 millimolar, so that's going to go up top here for S. The only thing that we need to know is our t value, our t-statistic. How do we find that? Well, to achieve that, we go to a table that looks like this. What this is a table of the t-statistic. You'll find this in your textbook for your analytical chemistry class. If you're taking an exam, it would be printed on the exam. Maybe it wouldn't look exactly like the one I'm showing you here. It might have less numbers, but something of the sort would be there. You don't have to memorize these numbers essentially ever, but this is the t values, the student's t values basically. To use this particular chart, we need to know 2 things. We need to know the confidence level that we desire. We need to know the degrees of freedom. In the problem, it's going to tell you the confidence level. As I already stated for this problem, we're going to use the 95% confidence level, which means we want to use values out of this column, okay? Now the degrees of freedom, you're going to have to figure that out on your own. But fortunately, it's pretty easy how to figure out degrees of freedom, because for this confidence interval calculation, the degrees of freedom is equal to n minus 1, where n is the number of data points in the pool of data. So here we had 5 replicate measurements, so 5 minus 1 is 4. So we have 4 degrees of freedom. And consequently, the value that I would like to use for my t-statistic in this equation has a value of 2.776. So I'm going to write that in. That's going to allow us to complete this calculation here in a second. But before we do, let's take another glance at this table. Let's see how the value of the t-statistic changes with confidence level and numbers of degrees of freedom. Let's consider confidence level first. So across any row of data, what do we see as the trend in the value of the t-statistic? Well, here, these numbers are all less than 1, and by the time we get out here, a lot of them are over 3, 4, and boy, this one at the top here is 636. So it seems like the numbers really increase as you go from left to right. Does that make sense? I would argue it does, okay? Let's think about this. As we go from left to right, the confidence level increases substantially. Here it's 50%. That's essentially a coin flip, whether or not your true mean lies in the range. Here it's 99.9%. Only 1 out of 1,000 times would your true population mean not lie within the range you're going to define out here. Okay, so this is a very high standard. Consequently, the t-statistic gets bigger. And that makes sense mathematically, because if we look back to the equation, the bigger t is, the wider or larger this range gets. Okay, so the bigger the range around the mean gets, the bigger t. Makes a lot of sense, okay? Let's now look at the trend down a column. Let's choose 90% just for reference here. You could choose any of them, you find the same trend. As the number of degrees of freedom increases, the value of t decreases. It gets smaller and smaller and smaller, okay? What that functionally means is if this gets smaller, the range gets smaller. So the higher degrees of freedom, that range about the mean will decrease. That also makes a lot of sense, because what is degrees of freedom linked to? It's linked directly to the number of replicate trials that you compute your average from. Makes a lot of sense that if you only have 3 replicate trials, you don't have a whole lot of confidence in your experimental mean being close to the true mean. But if I did this experiment 100,000 times, I'm going to have a lot of confidence if I average all those numbers together that the result I should get should be very close to the true mean. Okay, so that's why we see the decrease. The reason why I'm bringing this up is because oftentimes your instructor might give you conceptual problems that you have to think about how to make your confidence interval smaller. Okay, what that basically means mathematically is you need to make this term out here on the right, the range, smaller. So how can you do that? Well, t can be made smaller. Maybe your standard deviation is made smaller if you can improve your technique or use a different method that has a smaller standard deviation. Or else perhaps maybe you make n bigger. The easiest way to do it, if you don't have another method accessible, just make n bigger. If you make the number of replicate trials bigger, you kind of get 2 bonuses, right? One is this n gets bigger, so the range gets smaller just because of the direct result of the computation. But if you make n bigger, degrees of freedom gets bigger, so your t-statistic's also going to get smaller, all right? So more replicate analysis is usually good to make your confidence intervals smaller. But remember the mathematics, and you can justify reductions in this range, based upon the form of this equation, all right? You need to be a little bit quantitative with it, right? You know that, quadrupling n will have some effect upon the confidence interval, and you can kind of compute that in your head if you would like. I won't give you the exact answer, but you can compute it in your head. So anyway, moving back to our sample problem, because I did want to finish that off, right? It's important to be able to calculate these in addition to understanding the trends. So if I'm going to finish off this problem down here at the bottom, I can now go to my calculator, do the math here, and if I do that, I find my 95% confidence interval as being equal to 52.1 plus or minus 2.7 millimolar. And I'm going to leave it with this number of significant digits for right now, okay? Now what does this mean? That's our confidence interval. What does it mean? Well, I like to think of it this way. I like to draw myself a little sliding scale. At the center of that sliding scale, put my experimental mean. I can have higher values or I can have lower values. This is the magnitude of the value axis, basically. And the fact that I computed this interval tells me one limit of my range is 52.1 plus 2.7. That of course yields 54.8 millimolar. That would be the top of my range. Alternatively, I could subtract my range which makes the minima of my range 49.4 millimolars. So what this basically says then is I am 95% sure, or 95% certain, that the true mean, or the true concentration of the sample that I am analyzing, lies between these endpoints. It lies somewhere between 49.4 and 54.8 millimolar. That's where the true concentration should lie, and in the absence of systematic error or something just being wrong with my experiment, my true mean lies in this range. And that's the meaning of my confidence interval. Okay? Now if we go back and we look at the previous worksheet, we can see that that true concentration was 50. And these were my n equals 5 replicate measurements on average. Now average wasn't 50, but because we defined our interval as the average plus or minus that range, we can see that 50 does lie inside that range, and sure enough, our true measurement, or our true value, lies within that confidence interval range. Okay? So what that means then, functionally, is even though we never got 50 here, our average wasn't 50, our analysis was essentially correct, because the true value lied within our 95% confidence range. So again, the key ideas here are how to calculate or compute the confidence interval. We also want to know what a confidence interval is, what it means in terms of this range business that we talked about. And we also want to understand that when we state a confidence interval, we have a specified probability of finding the true population mean within that range. So we need to understand the difference between the population mean and the measurement data set mean. Okay, that's also an important concept here. So I hope that you've enjoyed this video and you're understanding the confidence intervals. We'll see you next time.